Good morning, everybody. It is June 23rd, 2019, just after 9 o'clock. It's about time I gave an update video overview of my solar system. I've done one other part for this, part one, where I walked around the outside, the solar panels and the inverter that I've got mounted outside. Kind of gave an overview of how the system works. And so this one I'm going to focus on inside my garage. This is the off-grid portion of my solar system. I've got my batteries and my off-grid inverter. So what we're looking at here is my pack of batteries. The yellow ones are lithium iron phosphate. They're 400 amp Winstons. These are circa 2008. They're pretty old. I got these from a guy on a forum who had them sitting in his garage for a long time with best intentions of doing something with it, never did, and was just looking for somebody to come get them, so I got them. The blue ones are 180 amp hour Sky Energy lithium iron phosphate. These ones I got from another guy online who had converted his Saturn Vue about 5 years ago to fully electric, and then about a year or two ago he bought a Model X and didn't really need the Vue anymore, so he took all the batteries out and set them in his basement for about a year. There was 48 of them, I believe, and he had a battery management system on it, and he kept the battery management boards on the majority of the cells, and over time the battery management drained all but about 17 of the 48 cells to 0 volts. The remaining 17 either had anywhere from half of a volt up to maybe 2 volts. I was lucky enough to be able to salvage them, and this is what I'm left with. So it worked out pretty good. And then on the left we have a complete Nissan Leaf pack plus one. The lithium iron phosphates, they have a nominal voltage of about 3.35 volts, so to put 16 of those in series gives me my required voltage. The Leaf cells from the battery pack, I bought an entire battery pack on eBay. There was 48 of them. Each one of those has a nominal voltage of about 7.65 volts, so to get this required voltage I had to put 7 of them together. I had to buy a 49th little can, if you will, so that I could do a 7 series, 7 parallel configuration. Each of those little cans are roughly 60 amp hours, and then 7 of them in series gives you 420 amp hours. No, that's not true. 7 of them in parallel gives you 420 amp hours. If you add up 400 amp hours from the Winstons, 180 amp hours from the Sky Energies, and the 420 amp hours from the Nissan Leaf pack, you end up with 1000 amp hours. 1000 amp hours at nominal voltage of 53.6 is 53.6 kilowatt hours. I'm not running any kind of BMS on this at all. Not on the Winston, not on the lithium iron phosphates, and not on the Leaf cells. If you don't know what you're doing, this could be a dangerous thing, but I kind of know what I'm doing. And the way to prevent any damages, I don't ever let it charge more than about 80%, and I don't let it charge below about 20%. The fully charged voltage of this system is 57.6 volts, and the minimum voltage is 40 volts. Under peak sun conditions, when I'm charging at the maximum amount and I haven't used the battery, it will charge to 57.6 volts, and at that time I've got a little relay that disconnects the charge. I'll get into that a little bit more. And under inopportune conditions, no sunlight and batteries are dead, the inverter will shut the system down when it hits 40 volts. So the inverter that I'm using is an Ames Power excuse me, an Ames Power 12 kilowatt hour, 12 kilowatt inverter, 12 kilowatts continuous. It'll actually do 36,000 watts briefly for, I think it's 5 or 10 seconds, and then it's sort of a linear function down from there to the continuous 12 kilowatts. For my meters, I got this clever little device over here on the side. I got this off of Amazon. It is cheap, and it'll give you the current voltage, current amps, be it charge or discharge. You can see right now how it's sort of fluctuating between charging with a negative, discharging with a positive. That's because the well pump is on right now. You're going to see the well pump kick off here in a second. Then the third readout, there, see how it went up to negative. So now it's saying negative. That means that the solar panels are putting out more energy than either the house or the garage is consuming by about 35 to 40 amps. That's what's charging into the battery right now. And then down below you can see about two or so kilowatts coming in from the solar panels. Then underneath that, it's got a little red deal that says charge. That'll go green and say discharge. And that next to that, it gives you the total amp hours that's available. So you can think of that like a fuel gauge in your car. I'd mentioned that I don't charge more than 80%. So 800 is about as high as I'll ever let that go. And yeah, right now it's at 600. I actually charged both electric cars yesterday, and it ran the batteries down pretty low. So currently on the left of that you can see a little battery thing, and it's 25% is what it's calculating that we have in the battery pack. Now this isn't scientific equipment. It's just rough, and it's good enough just to kind of let me know where I am. And I base all my decisions on whether I'm grid tied or off grid, off that meter basically. And then down here I've got my favorite meter ever. This is a JLD 404. Right now it's displaying our voltage, system voltage, which is pretty close to the one I just showed you. And this also has an amp hour meter. This is wrong because the other day, a couple weeks ago, I ran my truck down pretty low, and I reset this just so I could see how many amp hours this meter says that I charged into the truck. It's just a little nerdy thing I did. I use the meter that's up on the wall for my main display. This is just kind of for other stuff. Behind the meter is a little DC-DC converter. Next to that is a little fuse block for 12 volt systems. This JLD runs off of 12 volts. That display I showed you runs off of 12 volts. And then next to that is a little switch that I have. I can flip that switch and shut down my solar output. And then next to that is the relay that's used to also shut down the solar output. So here's the way this works. It's a little bit odd. I don't really know what to call this system. I'm not grid tied in that I don't feed energy into the grid. I don't get paid by Meriwether Lewis Electric Co-op. I don't get paid by them anything if I'm overproducing and my batteries are charged. But I do have a connection to the grid, which I can switch whenever I feel the need. Whenever my batteries or my loads or the amount of sunshine dictates that I can do that. From the ceiling, you see I've got some wires coming down. The orange one, the Romex, that's coming in from a generator that I've got outside. It's a little 4 kilowatt diesel generator. Really noisy. I never turn the thing on. There's 2 grounds for green, and there's a couple black wires going in or going out, depending on the situation. At the moment, we've got power coming in from the solar panels, going in through the inverter, going through the magic that happens inside the inverter, and coming out those 4-aught cables and charging my battery. At nighttime, or when it's cloudy, or when I've got 2 cars charging and the dryer running, then the output, the loads required from the house and the garage are greater than what's coming in from the solar. So this will just automatically, internally, switch over from taking power in from the solar panels to taking power from the batteries, turning it over into 440 volts and sending it to the rest of the system. It's kind of magical the way that it works. There's no transfer switches or any kind of switching device like that. It's all just done internally. It has to do with whether the AC voltage coming in goes through the transformer and gets rectified into DC voltage, or whether the DC voltage goes in through the inverter and gets inverted and then out that same transformer into the system. This inverter also provides the 60 Hertz waveform that the grid-tied Fronius inverter outside needs in order to run. There's a UL requirement, I can't think what it's called, but it's UL something or other, and it requires that all grid-tied solar devices have to have a 60 Hertz signal in order to run. If they lose that 60 Hertz signal, then they shut down almost instantly, and that's to, quote, save the linesmen if a power lines go down during a sunny day. I don't know that any linesmen have ever been injured by a power failure or by the grid being down and solar panels being up. I don't think that's ever happened, but who knows? What do I know? So that leads us to one problem of having a system like this, where we've got an grid-tied inverter backfeeding a off-grid inverter and charging DC batteries. There is actually a charger inside this inverter. If I were to run the line from the grid into the input side of this inverter, there's a charger inside that would charge these batteries from the grid. I don't do that. If I did do that, that circuit would monitor the voltage of the batteries and shut down the charging when the batteries reach their peak. Since I'm not doing it that way, since I'm just running energy straight from the solar panels outside straight into this inverter, there's no mechanism to stop charging. So theoretically, as long as the sun is out and these batteries are full, it's just going to keep on pumping voltage into these batteries, and that's not good. Overcharged lithium batteries, in particular the leaf cells, become very dangerous. They can start a pretty big fire, very hot fire. So what I've got going on, this little JLD monitors my voltage for me. Whenever that JLD sees 57.5 volts, it's got a little internal relay that will energize this relay, which goes out that line right there and sends 12 volts to a contactor that I've got outside in a box that will disconnect the solar panels from this system. So when that hits 57.5 volts, that contactor will trip, disconnect the power disconnect that 50 Hertz to the grid-tied inverter, disconnects the power from it, and the grid-tied inverter will shut down. Whenever the voltage on the JLD reaches, what do I have it set for? 56 volts, I think, about a volt and a half difference. Whenever it reaches that 56 and a half, the relay will open and the contactor will close. It's a normally closed contactor, or it's normally open contactor, but the contactor will close anyway, and that will give this 60 Hertz system, the 60 Hertz signal, back to the grid-tied inverter. 300 seconds later, the grid-tied inverter comes back up and will charge the batteries again, and it'll just cycle back and forth throughout the day as long as the batteries are charged until we lose solar, until the sun goes down, at which time it'll get really close to being fully charged, and then it'll just run the systems through the night. Last month, May, I was actually off grid for the majority of the month, and I ended up with a $44 electric bill, $8 of which was actually my electric usage. I have a $35 connection fee from Meriwether Lewis with taxes and fees and all that other good stuff. So $8 out of 44 was actually what I paid for my electricity. The rest of it was connection charges and taxes. So why would I continue to do that? Why not just go off grid completely? There's a couple reasons. First of all, that diesel generator, as I mentioned, is noisy, really noisy, and there's maintenance involved with it, and it doesn't have an auto start feature, so I'd have to monitor the system pretty close. Go outside, start the thing, monitor it some more, wait till the batteries charge up, and then turn it back off. There's no need to go through all that. I can just keep a grid connection. The grid is quiet, the grid's reliable. There is that $35 a month connection fee, but I think it's worth it. If this inverter should ever stop working, or the inverter outside would ever stop working, or I need to add some batteries to this system, or have a failure of one of the batteries, if I need to do any kind of maintenance to this system in the garage, I can shut it down completely and reconnect to the grid and have good, reliable, clean power for as long as I need it until I make the necessary repairs, and then I can switch it back up again. Now I've got a few different methods of doing this, and I made a little chart to try and explain this. The off-grid inverter outside, the Fronius off-grid inverter, it feeds into a little distribution block, a little three-way distribution block. Let's see if this works for us. Okay, so lower right, we've got the solar panels are sitting outside. It feeds into that little distribution block on the bottom. The grid on the upper right comes into the main breaker in the house, goes through a 200 amp service connection. The garage is also connected to the little distribution block on the bottom, and then the third output of the distribution block goes into a 100 amp fuse in the house. So in this way, I've got three options. I can be completely off grid. If I wanted to do that, I would switch off the 200 amp main service connection, disconnecting myself from the grid. The inverter and all these batteries in the garage would feed in through the junction box, backfeed through that 100 amp service sub-panel circuit breaker, and run the house. The solar panels would do what they do. If it's during the day, they would charge. They would feed power into the house, run all the circuits in there, feed power into the garage, run the circuits in there, and if there's anything left, it'll charge the batteries. That's what we've got going now. At nighttime, there wouldn't be any solar, so all the batteries would feed the inverter, and it would come from the garage, backfeed into that little junction box, backfeed through the 100 amp circuit breaker, and feed all the loads of the garage, or loads of the house. If it's been cloudy for a few days, like last, or I've charged all my electric cars and my battery bank is low, I can switch it so that the garage only is off-grid. And the way that would work is I would have the 200 amp service on, the 100 amp sub-panel breaker off, and then power would feed from the solar panels through the junction box into the garage and charge my batteries. If I wanted to be off-grid completely, which I probably have to do in the winter sometimes, I can turn there's a 60 amp breaker in the garage that the inverter goes through. I would turn that 60 amp breaker off, have the grid 200 amp breaker on, and have the 100 amp sub-panel breaker on. And in that way, the grid would come in through the 200 amp service, feed the house, feed the garage, and give a little 60 hertz signal to my grid-tied inverter on the solar panels, and I would be able to have solar coming in. I don't know what exactly would happen is if I had a lot of solar coming in and I was fully on the grid. My meter isn't a smart meter, so from what I understand is it doesn't count backwards, it just counts amps. It doesn't know if they're coming in or going out, so if I was actually feeding the grid with solar, I think it would just increase my kilowatt hour usage, and I'd end up paying paying for that as well. So I wouldn't do that. If there was enough sun to provide more power than I'm using, then I would just either turn the garage off grid or turn the house and the garage off grid and let the solar panels charge my batteries. And let's see, what else to say about this? So this Ames Power off-grid inverter, I've had it for about since November, and it's been reliable, and it's done fairly well. There's a few things I don't like about it. You can hear the fans. That's not so much a problem for me because it's out here in the garage, so I can't hear it in the house. The fans are kind of noisy. The output isn't the best. Instead of doing the 220, 224 that the grid provides, this does about, I'm sorry, not 220. This does about 220 to 230. So all my 110 circuits, like the lights that I've got on in here now, instead of getting 124 volts like they would normally see from the grid, they only get about 110 to 114, and that fluctuates, and it makes the lights kind of flicker, which is it's kind of annoying. I don't think it causes damage, but it is annoying. The other annoying thing is the output frequency of this isn't exactly 60. It's about 59.9, and that the digital clock on my oven runs off of that frequency. So every week or so I have to adjust the clock. But that's just a minor inconvenience. It's not that big of a deal. But those are the kind of three gripes I have. The frequency's wrong. The voltage, the AC voltage, is a little bit unstable, and then the fans are noisy. But other than that, I really like the inverter. I like how it's working. This isn't. If I wanted to truly be off-grid, this inverter wouldn't really cut it. During the day when the sun's fully out and I'm getting 5,000 or 6,000 watts from that, I can have both cars charging, and run other loads and everything's fine. But at night, if I have both cars charging and then someone wants to take a shower, then the electric water heater comes on, and the well pump runs, and it doesn't exactly overload the system, but it overworks it, and I don't want to do that. I want to have this thing working less hard to hopefully preserve its life. As far as loads go, now that I'm going to talk about amperage draws, and bear in mind that I'm talking at the nominal voltage of 53, whatever I said, 53 volts, not 240 or 110 volts. So if I say something pulls 100 amps, I'm talking 100 amps at 53 volts, not 100 amps at 110 or 220. And for the sake of math, I just assume it's 50 volts because 50 is easier to multiply than 53. So when I've got my truck plugged in, it pulls about 45 amps. The electric smart car I've got that charger turned down, so it pulls about 45 amps also. The water heater pulls about 100 amps. The clothes dryer pulls about 100 amps. The well pump, when it's running, is about 45 amps, but during startup it can pull well over 130 amps. So you can see that if I've got both cars charging, that's 90 amps. Then the dryer's on, that's another 100, 190. Then somebody takes a shower and the water heater kicks on, that's another 100 amps, and it overloads everything pretty quickly. The other issue I have is that my wife and I both drive electric cars, and electric cars consume a tremendous amount of energy. Now if you compare that to the amount of energy that the